This is part 2 of my lecture on galaxies. In part 1, I talked about normal galaxies, galaxy motions, and the expansion of the universe. In this video, I'll describe active galaxies and what they reveal about the formation and evolution of galaxies. Here is a spiral galaxy that should look different to you than the ones you've seen before. In a normal spiral galaxy, the light we see comes from stars in the bulge and the disk. Here, the central region is unusually bright. Some spirals have big central bulges, but they're not this luminous. If we could obtain a higher resolution image of this galaxy, we'd find that the luminous region is smaller than it appears here. In fact, most of the light is coming from the very center of the galaxy. It's not coming from stars, but from gas. What's the gas doing that's making it so bright? I won't give that away just yet. I'll let you think about it. Here is another unusual galaxy. This one's elliptical. Remember, ellipticals normally don't have any structure. They look like smooth, featureless balls. Well, this one's got some structure. It's got a jet extending from the center all the way to the outer regions. This jet emits X-rays and visible light, but it's particularly bright in the radio. That makes this galaxy, M87, a radio galaxy. If we zoom into the central region of M87, we see a disk. This is not the type of disk that contains spiral arms, stars, and dust. It's like the disk of gas we find at the very center of the Milky Way, but much more luminous. We can see that it's blue shifted on one side and red shifted on the other side. So it's spinning rapidly. Here is another elliptical galaxy with an even larger jet. Here also we see a disk that lies perpendicular to the jet at the very center of the galaxy. And here is Cygnus A. The image on the left shows a galaxy that looks like it's neither a spiral nor an elliptical. It's got dust, yellow regions, and blue regions, but no spiral arms, and so you could say it's a disturbed spiral. All of that lies at the center of the radio image shown at the right. Cygnus A is one of the brightest radio sources in the sky, even though it's 500 million light years away. Almost all of the radio waves come not from the galaxy itself, but from these enormous jets being ejected from the very center of the galaxy. The jets are traveling at close to the speed of light. Having covered Seyferts and radio galaxies, let's look at quasars. The term quasar is short for quasi-stellar radio source. That means it looks like a star, but it has strong radio emission. The image shown here has two objects that look like stars. One of them is a star in our galaxy. The other one is a quasar 9 billion light years away. Can you tell which is which? I can't. Remember, the universe is less than 14 billion years old. That means the light we're seeing from the quasar was released when the universe itself was less than 5 billion years old. The nearest active quasar is over 2 billion light years away. It appears that quasars live inside galaxies. Some of them are so far away that we don't see the host galaxy. In other cases, we do see the surrounding material. The quasar itself is the central nucleus of the galaxy, where there's an extremely luminous disk of gas. What do Seyferts, radio galaxies, and quasars have in common? All of them have a luminous disk of gas at the very center. Why is the gas so luminous? It's heated to millions of degrees as it falls into a supermassive black hole. The Milky Way is not the only galaxy with a supermassive black hole at its core. All large galaxies seem to have one. However, the black hole at the heart of a Seyfert, radio galaxy, or quasar is more well-fed than the Milky Way's black hole. There's much more gas falling into the black hole of an active galaxy than in a normal galaxy, such as the Milky Way. In the case of radio galaxies and quasars, some of the gas particles that don't get sucked in are turned into jets that are shot out at high speed. Why is it that some galaxies have a lot of gas feeding the central black hole while others don't? Before you can understand that, you have to learn a bit about how galaxies formed and how they evolve. When the universe was young, matter would have been distributed pretty smoothly throughout, but there was slightly more matter in some places than others. Due to gravity, these regions became more and more dense. Matter left the medium density regions for the high density regions, and eventually there were no medium density regions. There were just high density regions and empty regions called voids. The high density regions are where we find superclusters. Inside the superclusters are clusters and groups, and inside those are galaxies. All of this is theory. Here are snapshots of a simulation showing how the universe could have evolved with time. Now let's go from theory to data. When we look at the distant universe, we see a whole bunch of small, irregular galaxies. Many of these appear to be colliding together. Remember, when we look into the distance, we're also looking into the past. This is not how these galaxies appear today. This is how they appeared billions of years ago. In fact, these galaxies might not even exist today. They may have evolved into something else. Let's switch back to theory for a minute and look at how a galaxy like ours might have formed. We zoom in on a filament, which is a long chain of matter, and see a bunch of tiny, irregular galaxies. These collide together to make small disk galaxies. Spiral arms start to form in these galaxies. A few of these have collided together to make a larger spiral galaxy. Here comes another decent-sized spiral galaxy. They swing by each other and eventually merge to form one massive spiral galaxy like the Milky Way. Most of the stars will find their way to the central region to form a bulge. The leftover gas will form a new disk around the bulge. Our galaxy continues to eat some of its companions. There used to be a galaxy called the Sagittarius dwarf spheroidal, but as it has orbited the Milky Way, it's been slowly getting torn apart and eaten. Part of the core is still intact, but there is debris scattered all around the Milky Way. So large galaxies like ours started forming billions of years ago from collisions between smaller galaxies, but continue to eat small companions today. Here and there in the local universe, we see two or more large galaxies colliding. This is called a major merger. Here's Stephan's quintet. Two of the galaxies have already started merging together, and two more are going to join them, and finally, the last one. Here are two spirals that have already plowed through each other at least once. The full merger is not complete. The inside is a mess, and there are long tails left behind. When we zoom in, we see the bulges from the two individual galaxies. The spiral arms have lost their identity. There's lots of dust. There are many glowing gas clouds in bright blue regions. This suggests that the collision has triggered lots of new star formation. Here are two other spirals colliding. Both galaxies look brighter than normal, and one looks quite blue, indicating that these are bursting with new star formation. At this rate, they'll quickly consume all of their gas, and after that, no new stars will form. Could something like this happen to our own galaxy? We do have another large spiral nearby. In fact, the Andromeda Galaxy is even larger than the Milky Way, and it appears to be headed our way. Various teams of astronomers have simulated what could happen in the future. Here are snapshots from one of them. In 2 billion years, Andromeda will look much larger in the sky. In 3.75 billion years, Andromeda looks much larger, but the two galaxies haven't started colliding yet. Then the merger begins. The stars of the two galaxies will slip right past each other, so the Sun will most likely not collide with a single star from the Andromeda Galaxy. But the gas clouds will collide violently. This will trigger bursts of new star formation. We see bright nebulae and young blue stars everywhere. Then the starburst activity decreases. New stars are still forming, but not with the same intensity. The sky is not as bright as it was before. 5 billion years from now, the disks of the two galaxies have been completely destroyed. The merger has made the stars orbit in random directions. There's much less new star formation. There are just faint star-forming regions here and there. Eventually, the merger is complete. We live in one huge galaxy. All the gas has been consumed. No new stars are born. Existing stars go through their lives. The blue stars are all dead. Only yellow, orange, and red stars are left. The stars orbit in random directions. What do we call this type of galaxy? It's an elliptical. It appears that the collision between two large spirals will produce an elliptical. Now let's watch an animation showing the collision from beginning to end. There's the Milky Way, and Andromeda, and a third galaxy called Triangulum. The Milky Way and Andromeda initially dance around each other and collide for the first time around 3.8 billion years from now. The two galaxies plow right through each other, and eventually gravity pulls them back together. The stars don't collide, but they're flung every which way. Their orbits get randomized. After a couple more collisions, the two spirals have turned into one huge elliptical galaxy. The Triangulum galaxy remains unscathed, but eventually it will also get eaten. Some ellipticals still contain the undigested remains of galaxies they've eaten. Ellipticals normally don't have dust, but this one appears to. It could have recently eaten a spiral, or it could have formed from the collision of two or more spirals. At the center, there are two cores where gas appears to be falling into two separate black holes. And here is a large cluster of galaxies. There appears to be one large elliptical in the middle. But it's not perfectly smooth. It's got a whole bunch of subcomponents. These are the galaxies it just ate for lunch. It hasn't fully digested them yet. Here is another elliptical that has clearly eaten a spiral recently. This one also happens to be an active galaxy. Some of the gas that isn't eaten by the central black hole is ejected out in huge radio jets. I had mentioned earlier that all massive galaxies appear to have a black hole. It turns out that the more massive the galaxy is, the more massive the black hole is at the center. This may seem obvious to you, but it came as a huge surprise to the people that discovered it. That's because the black hole at the center of a galaxy is tiny compared to the galaxy itself. The central black hole has no effect gravitationally on the galaxy as a whole. But apparently, the formation of the black hole is related to the formation of the galaxy. By the time a galaxy gets to a certain size, it appears to have a black hole at the center. And when this galaxy combines with another galaxy that's equally large, the two black holes of the individual galaxies also merge together. So eventually, the black hole at the center of the Milky Way should merge with the black hole at the center of the Andromeda galaxy. Now let's put everything we've learned about galaxies together. Here is all of galaxy evolution in one slide. Time increases to the right. Initially, there were just a whole bunch of tiny galaxies. Then these merged together to form a decent-sized galaxy. At some point, a black hole showed up at the center of this galaxy. And there's a lot of gas falling into the black hole. We call this a quasar. Now, this can go in one of two ways. If there's a major merger that randomizes the orbits of the stars and turns whatever gas is available quickly into new stars, we end up with an elliptical galaxy. If there's still some gas feeding the black hole in the center, it's a radio galaxy. Eventually, the black hole has no food left, and we are left with the normal elliptical galaxy. If a quasar-host galaxy continues to eat small galaxies slowly so that the gas doesn't all get used up, we end up with a spiral galaxy. For a while, there's still gas falling into the black hole. We call this a Seyfert. Eventually, the gas at the center is consumed and the black hole becomes dormant. We end up with a normal spiral galaxy, like the Milky Way. There's still gas in the spiral arms, forming a few new stars every year, but none at the center feeding the black hole. This galaxy could still merge with another big spiral to make an elliptical. The nucleus could even become active again for a while if there's gas available near the center to feed the black hole. What this picture of galaxy evolution suggests is that the Milky Way could have been a quasar in the distant past. Quasars are only found in the distant universe. That means they only existed in the past. If you could instantly transport yourself to something that looks to us like a quasar, you wouldn't find yourself in a quasar. You'd probably find yourself in a normal spiral or a normal elliptical. And from there, if you looked at the Milky Way, you'd be looking at what the Milky Way used to be, not what it is now. You could be looking at a quasar.